Okay, I'd like to begin the next section of this webinar, and we're going to talk about simulation to assist in process creation. So we finally get to chapter 7 of our book after we've done the heuristics for process design. Okay, so moving on. Okay, we do this much in 5 lectures. Our course uses Aspen Plus as a process simulator. We begin with a focus on mass balances. The students have seen some of this already in the freshman course. We expand this to discuss the degrees of freedom, the design specifications, the recycle loops, bubble and dew point calculations. Most of this is a review in many respects. We are also showing how to use the SuperPro Designer simulator for batch processes. Okay, and we have the specific bioprocess example, the TPA process. And we talk about the batch and the cycle times and the Gantt chart for scheduling and the bottlenecks that occur. Okay, moving on. So we start with a simple mixer problem, okay, and it allows us to discuss the degree of freedom ideas and the design specification ideas. The students need to note the number of variables and the number of equations the relationship between them. This helps them understand how many pieces of information they need to supply. And this can also be used to show them how to trade information and unknowns. Okay. We also use this to illustrate the design specification feature in the Aspen Plus process simulator. Students can find this helpful to solve the problem backward. How do you make an upstream adjustment when you have a downstream goal? So we do an example, and most people do this kind of thing. Okay, you got two streams, S1 and S2, and you would like to be able to specify an outlet temperature. So you measure the outlet temperature, you have some kind of a solver that has a specification, okay, and you adjust the flow rate of S2, and you iterate around doing that. That's a typical kind of an example. Okay, now what next? We work through a complete example, okay? And our example involves the synthesis of a very well-known process started by Jim Douglas in his book in 1988, the toluene hydrodealkylation process, okay? And we show the students a simulation containing all of the process synthesis operations. And we, what we taught them at the beginning of the semester in chapter 2. Okay, these are the operations. I won't read them to you. The students can solve the mass balance and stoichiometry for the overall flow rates. So in this case, you would have hydrogen coming in. You would have toluene coming in. You're going to dealkylate. You are going to then make benzene and methane. Okay, so it goes into the process, and you can then determine what the product flows are going to be. I won't go through all that. That's just a mass balance. Now, when it comes to simulating the reactor, we have them do it simply just with a stoichiometric simulator, okay, as opposed to a plug flow reactor. We can do that later, but we don't do that at this point. The separation units, okay, we have them look at that, and I'll have some things to say about how we do the separation units. And we do have, in this case, a recycle stream, which has the unreacted toluene, and that comes back to get mixed. So they're aware of this at the outset. And now we go through and teach them things they're going to need to know. All right, first thing is we want them to be aware of the separation modules that are available. And the simplest one is the split fraction method, SEP2 in Aspen, okay? And then, of course, the thing here is you're specifying the fraction of a component that's going to go into one of the product streams, okay? It's a very simple idea. This doesn't incorporate any thermodynamic calculations. It's a method that returns information about the number of trays. It does not return information about the number of trays or the reflux ratio. All right, now then we tell them about something called dist woo, which interestingly enough, we got from the FlowTrans simulator when we built Aspen. I was involved in that. Okay, dist woo does a more complete series of calculations. All right, and the user has to give more input. This leads to a discussion about the choice of the heavy key component and the light key, which they learn about in the separations course. The students can use this to learn more about the proposed column. How many stages does it have? What's the reflux ratio? What's the minimum reflux ratio? What's the heat duty in the condenser and in the reboiler and so on? All right, so we do that with them first. Now, they do a series of homework problems like this. Okay, they do flash with recycle. Okay, they adjust the ratio between the product and the recycle stream. Well, let me tell you a little bit about this process. It's a very simple process. You got a stream here at 85 degrees centigrade, 100 psi. You just have these hydrocarbons, methane, ethane, propane, right on to 1,3-butadiene, 6 components. Okay, you take it, you then drop the pressure from, 100 to whatever you like. All right, here it's shown for 25 psia. You can have the temperature be 5 degrees centigrade, or they can solve the problem with different values here. Okay, now you got an overhead stream coming from a flash vessel. It's at equilibrium with the liquid. The liquid comes down as bottoms. All right, you're putting some heat in or you're taking some heat out. Good enough. And then you have a product coming off. Okay, whatever this bottoms is, a portion of it goes this way. The rest of it gets pumped, and it gets pumped back up to 100 psia. And all right, it gets mixed together, and that's the problem. All right, so they play with this problem. It's a very nice problem. One of the interesting things is because these streams are in equilibrium, doesn't matter how much, what fraction goes off as product, you always get the same overhead and the same product. And that's an important lesson for them. Okay, now then we move to another homework problem. We've taught them about how to synthesize the toluene hydrodealkylation process, the HDA process. Okay, so what we're asking them to do is take the feed stream for that process. And we're telling them what the recycle is. Often when you're going to solve a process, when you're doing a process synthesis, you just guess at what the recycle will be for the toluene, the unreacted toluene. And you have a gassy recycle, which involves some hydrogen feed and then some of the methane product. That comes back. You guess at what that will be. They mix it together. They heat it up to reaction temperature right here. They run the reactor. Okay, now they quench then with a cold liquid. You take that and you cool that liquid down from this particular temperature, which has been spec'd, and you then come down to here. You remove more of the heat with cooling water to 100 degrees Fahrenheit, and you now take vapor off and you take liquid here. This liquid goes to this liquid separation system, the distillation columns. Okay, over here, you send back just the right amount to get the temperature down to 1150 degrees Fahrenheit. So that's a very nice kind of a problem for them to learn how to use the design specs, okay, and do the recycle calculations that are necessary. Then we take it to another problem, which does the separation section, just to get them into this, even before we've taught that. Danny's going to teach you, going to show you how he teaches separation train synthesis in just a moment. Okay, we just get them into it even before we teach them it. We tell them, okay, look, you see, here's your stream coming off from that reactor. Here it is, okay? It's got hydrogen, methane, benzene, toluene, biphenyl, okay? All right, so what you're going to do is you're going to take a product off. You have to have a product of hydrogen and methane mostly, and you have to have a product of mostly benzene, and you have to have a product of mostly toluene. Okay, now you can do it in one of two ways. You can open this valve. You can close that valve, okay? If you open this one, close this one, all right? Close this one, open this one. You're going to take the light components off first, like this, okay? Alternatively, just do it in reverse. Open this one, close that one, Okay, open this, close this one, open this one, and now you take the heavy components off first, just to give them that experience even before they've learned anything about separation trains. Okay, so that's that. Now, let me see my timing now. This is very important. 25, just a second. I got to see that. Okay, should be okay. Right. All right, here we go. Now, how do we teach them simulation? Okay, to use the process simulators. Well, we teach them with the multimedia. Danny pointed that out. And what I'd like to do now is to show you how we do that. I think I hear somebody speaking. Is there a problem here? Okay. Anyway, so I'm going to skip right through this quickly and get to the multimedia. Now I have to go over to here and I have to go to here. Okay, here we are for the multimedia now, using process simulators in chemical engineering. Okay, and in the slides that I didn't show you, it shows you just exactly what the URL is to get to this multimedia. Okay, I just want to mention here, this was done back several years ago. Okay, but it had to be updated just this last year. And it was done by an outstanding senior student, Chase Novak, and I wanted to give him credit for many of the changes that were made. Okay, so now I want to show you this. I want to show you now, okay, here's the table of contents, all right? The multimedia, well, it's a very nice introduction, and it closely parallels the beginning of chapter 7. Okay, so if people are using this, I recommend you look at that. I don't have time to show it to you. Principles of flow sheet simulation. Okay, there are many topics that are covered in here, but from my point of view, the convergence section is probably most important. The design specs, it shows the students how to do the design specifications, how to do the recycle. There are many different subjects under recycle. Okay, that's an important part. All right, so I wanted to point that out. Okay, now let me bring this back up over here. I gotta hold it. I gotta do this. I gotta do that. Okay, now notice there's a whole section on separators and a whole section on heat exchangers and pumps and compressors and expanders and chemical reactors. Okay, so I don't have time to show you all of that. But what I'm going to do is I'm just going to take you down into separators. I'm going to show you something very simple because it's quick to show. And I'll go down to phase equilibrium and flash, and I'll go to the flash right there. And I'm going to do the introduction in video right now. Okay, here we go. Let me move this out of the way. All right. And what we're doing is simply showing a simple flash vessel. All right, flow rate, mole fractions of the feed, temperature of the feed, pressure of the feed. You got some heat coming in, or maybe it's coming out. Okay, you got temperature and pressure inside here. You got a vapor, liquid, vapor mole fractions, flow rate of liquid, so on. That should be in everything's at equilibrium. Now watch this.
In many chemical processes, flash vessels are inserted to provide an initial separation between the most volatile and least volatile species in liquid streams, which are often effluents from chemical reactors. Usually the streams at elevated pressures are flashed across a valve to produce vapor concentrated in the most volatile species. The vapor impinges upon a baffle plate to remove liquid droplets which fall into the liquid pool. As the vapor rises, small liquid droplets disengage and fall into the pool as well. Finally, a fine metallic mesh known as a demister permits the smallest droplets to coalesce and drop into the pool. It is common to allow the liquid pool to reside in the vessel for 5 to 10 minutes. This residence time permits occluded bubbles of vapor to leave the liquid. Most flash vessels, consequently, provide a complete separation of the vapor from the liquid phase, and thanks to the sufficiently large residence time, the phases leave the vessel in equilibrium. Many flash vessels are well insulated and operate adiabatically. When desirable, heat can be added or removed with cold or hot utilities in coils that are inserted into the liquid pool.
Okay, let me move on now. Okay, what we could do here is take a look at a typical flash vessel.
This video shows a flash vessel mounted on a concrete support. Notice that the feed enters midway up the vessel, with the vapor leaving in the pipe above and the liquid exiting in the pipe below.
Okay, I might say that we have a video like this from the major pieces of equipment throughout the multimedia. Okay, now you could see, just just a second. All right, press here I want to go there. Okay, this is just a diagram, the general diagram that shows for the flash 2 subroutine in Aspen, you have a vapor stream. Okay, you could have a heat stream, it's optional, so on, and liquid coming like this. Now watch this. Now we'll go to here. All right, now we're going to do this example really quickly. N-pentane and N-hexane, 130 degrees Fahrenheit, 73.5 psi, 1 pound mole per hour, flashed it to 120 degrees Fahrenheit, 13.23 psia. Okay, so I want to do that example. All right, so you could see the entire Aspen Plus tutorial for this.
Okay, so now we're going to show you how to run a simulation with a Flash 2 subroutine with the example that we just saw in the previous slides. So first, let's press new to create a new simulation. Double click new. And then we're going to go with this template that says general with English units, since we were given our temperatures in Fahrenheit and our pressures in pound per square inch in the example slide. Let's press create. All right, now Aspen will first take us to this property section and want us to specify our components right away. But I like to make my flow sheet first. So let's come down to this simulation tab and build our flow sheet first. All right, so now we can see that we're in our main flow sheet window. So let's start by putting our Flash 2 subroutine on the page. So come down to the separators section in the model palette, choose Flash 2, and place it on the flow sheet. All right, and that's the only block we're going to have in this simulation. So now we just need to specify the feed and product streams. So press the material stream, and we'll specify the feed stream first. So press on the red arrow going into the reactor, or sorry, not the reactor, going into the Flash 2 subroutine. Drag back and press again, and now we have our feed stream. Now we also need to specify the vapor overhead stream. So do the same thing, press and then release and press again. And then one more time to specify the liquid stream. All right, so now at this point, I like to make this flow sheet look a little bigger. So if you come up to the View tab and press Zoom to fit, it'll make your flow sheet zoom to a...
Okay, I'm going to quit at this point. You guys can come back to this at any point. The URL is readily available. And I'm going to just do one more thing here and then turn it over to Danny. Let me do this. Okay, now here what I'm going to do is just see only the input forms. Okay,
The
so
input form for Flash 2 is very simple. Only 2 specifications need to be made. They are chosen from temperature, pressure, vapor fraction, and heat duty. In this example, the flash temperature is set to 120 degrees Fahrenheit, and the flash pressure is set to 13.23 pounds per square inch absolute. Notice that the valid phases specification is left as the default selection of vapor liquid. In an ideal mixture such as this one, 2 liquid phases will not form.
quickly.
Here you can see the main portion of the input summary from the simulation. Here you can see a portion of the stream results for the simulation. As expected, the liquid phase contains a higher fraction of the heavier component, hexane, while the vapor phase contains a higher fraction of the lighter component, pentane. Here is a portion of the results for the Flash 2 block. Notice that the K value for the lighter component, pentane, is greater than the K value for the heavier component, hexane, as expected. Also notice that the difference in the enthalpy flow in and the enthalpy flow out is precisely the heat duty that is required for the process.
Okay, what I'm going to do now is separate, is jump away from this and come back to this quickly and do that. So we've just gone through this demonstration. For you, when you're looking at this later, there are the URLs for the Aspen multimedia and for the HiSys Unison multimedia. Okay, one last thing. Okay, I don't have time to go over this with you now, but Okay, you've seen what's involved in synthesizing the reactor section for the toluene for the tissue plasminogen activator process. Okay, so we take that particular flow sheet which we synthesized, and we're now going over to ProDesigner to do this. But I just want to mention this quickly. When we help the students do this in chapter 7, we just we show them how to do it for just 2 cultivators. Okay, leave the third one off. And they then see what happens when they run the simulation with just 2. And they can see there's the bottleneck unit. It's the second fermenter. They can see the cycle time, all of that. Then they're asked to do it on their own to add the third cultivator. That works very well. Okay, I'm going to stop sharing. Danny, I'm sorry I took a little of your time. Okay, and now you can take it.
Okay, thank you, Warren. Can you guys see my screen?
Yes.
All right. So what I'll discuss now is the 2-week segment taught at the Technion, which teaches the systematic design of separation trains. I will give you guys a 20-minute or so overview. Actually, I'll try and speed it up because we're running out of time. A 20 or so minute overview of the materials which we cover at the Technion in 4 hours of online lessons, 4 hours of class meetings with students, and 6 hours of active tutorials in which students solve problems for themselves. All of the materials that I will discuss now are taken from chapter 9 of our book. So, an overview of the 2-week sequence. Basically, in week 5, we teach zeotropic separation train sequencing, which involves the students becoming familiarized with the idea of the separation factor, to choose between alternative separation methods, using heuristics to narrow the design search space, and systematic design methods. We cover branch and bound and the marginal vapor rate method as ways of selecting from alternatives to arrive at the optimal sequence. In week 6, we teach azeotropic separation train sequencing, which involves principally enabling students to sketch their own residue curves, to define the feasible space for distillation columns in ternary diagrams, and then both homogeneous and heterogeneous system synthesis. Let me go into some details now. First, we'll start with the zeotropic separation train sequencing materials covered in week 5. Here is a list of instructional objectives. So you see here, we revisit first the separation methods that were covered in the heuristics part of the course. We then teach about the separation factor. Students should be able to use the separation factor to determine between alternative separation methods. We teach them to know how to apply heuristics to narrow the research of alternative separation sequences to what would be near optimal separation sequences. And for optimization, we teach either branch and bound or the marginal vapor rate method. So we start, like in most of the lectures, we start by presenting a problem and its solution. So here is a typical separation involving the separation of 6 components into 4 products. We have a mixed alkanes from propane all the way down to N-pentane. We want to make propane, N-butane, a mixture of all the butenes. Notice there are 3 of them, and N-pentane. These are the products that we would like to make. And we start off by actually showing the student the actual optimal design, which involves a column to separate the light components from the rest of the system, a second column to produce propane and 1-butene, a third column to separate the pentane as bottoms, and then a system of 2 columns involving extractive distillation using 4-Vorel to separate the butenes from the NC4, from the butane. Okay. Now the students are promised at the beginning of the lecture that they will be able to generate such a design themselves optimally by the end of the lecture, by the end of the teaching materials. Okay. So we start by teaching them about the separation methods, an overview, basically repeating the heuristics material, the idea that you can use either energy separating agents or mass separating agents or a combination, some details about separation equipment, optimal arrangement, and of course, we need to define the temperature and pressure conditions for each equipment item. The key is the definition of the separation factor in its simplest form. For an ideal system, it would be just the ratio of the K values, as we know, for the case of ideal distillation, but separation factor is also defined for more complex separation problems involving non-ideal separations, for example, requiring extractive distillation, or for liquid-liquid extraction. Now, why is the separation factor so important? Because basically it allows us, using the approach of Seider's, to determine what should be the separation factor for a separation system that is competing with ordinary distillation in order for it to be feasible. So what we see here, we see curves, which are the trade-off lines between either ordinary distillation, extractive distillation, and liquid-liquid extraction for given a value of alpha for ordinary distillation. For example, suppose we have an ordinary distillation which has an alpha, a separation factor of 1.6. What these curves tell us are what should be the minimum separation factor that would be achieved from an extractive distillation system that would compete with that ordinary distillation column, and also what should be the separation factor for a liquid-liquid extraction system. Why are these things important? Basically, these are target values of the separation factor, which we need to shoot for by selecting the appropriate mass separating agents. So these are actually guidelines for the design of suitable mass separating agents. That's why these curves are so important. Moving on to sequences of ordinary distillation. Well, it's a combinatorial thing, right? You have a certain number of products that you want to produce. Assuming that your system is comprised of ordinary distillation columns involving just 2 product streams, then for 2 products, you would need 1 tower, and there'd be 1 possible sequence, right? But if you have 3 products, you obviously need 2 towers, and there are 2 possible sequences, and so on. Once you get to 8 products, the numbers start to geometrically increase, which is the reason why you might want to consider heuristics to reduce the list of possible sequences that you need to go through by simulation to determine which would be most optimal. For example, here's the situation for 3 products. Okay, there are 2 possible sequences, either the direct or the indirect, which is why we need heuristics. So we then introduce the idea of heuristics to the students. There are a large number of heuristics that we consider. For example, we should consider removing unstable, corrosive, or chemical reactive components in the initial separation tower to save money, obviously. Another possible heuristic to consider is that we should try and consider the components in order of the greatest molar percentage in the feed. And another very important heuristic is to remove the products in decreasing order of relative volatility. This leads quite naturally to example problems presented to the students. For example, in a different a problem involving only 5 components that we need to separate into 5 products, the possible, and given of course that we have molar flow rates of all the components, and we can compute the relative volatilities between every component pair, we could, for example, use rule 4 that we showed previously, that is to remove the separation, remove the components in decreasing relative volatility. So recalling the relative volatilities presented previously, this naturally leads to 1 possible sequence where every tower is inserted in decreasing order of relative volatility. Or, for example, using rule 3, where we separate the products in decreasing presence in the feed composition, we would have a different sequence to consider. So we can generate a number of alternative sets of sequences just by heuristics. And these would, of course, be, we would be competing against each other in terms of costing. We will see later how this idea of heuristics can be very helpful, even if you want to do detailed design. For example, once we get to more complex separation systems where we may want to consider alternatives to ordinary distillation, then the number of sequences increases yet again. We had this NS computed by the combinatorial equation I showed before. If we want to consider different types of separators, different types of separation methods, for example, in contrast to ordinary distillation, we might want to consider extractive distillation, with, say, 2 alternative mass separating agents, we might want to consider liquid-liquid extraction. So, for example, if we had only 3 products and we want to consider both ordinary distillation, extractive distillation with 2 solvents, that's already 3 alternatives, and also liquid-liquid extraction with a 3rd solvent. Now, the number of types of separators are now 4. So we now calculate here on this equation, we would actually, instead of just 2 possible sequences that we saw before, we would actually require already 32 sequences. And these things have to be considered. And given the large number of alternatives that we would have to look at, obviously, we're not going to simulate all of these. Students do need to graduate at some point. So obviously, we don't want to overload them with 4 years of calculations. So let's go back to the original problem as promised to the students. At the beginning, we said to the students we would actually solve this. So we just go ahead and actually show how this is in fact solved. The same feed stream involving 6 components into 4 products. We, of course, have data for the boiling points of all of these components. We refer to them as components A to F now, with them listed in decreasing relative volatility. So let's suppose we're going to consider 2 alternative separation methods: ordinary distillation, extracted distillation using Fouverol. So we have 4 products. Yes, 4 products because we want propane, a mixed butane stream. That's B, C, and D together. B, D, and E, C separately, F separately. 4 products. So here we have 40 possible sequences that we have to look at. Unfortunately, that is not the correct answer because 1-butene is not consecutive with the other 2 butenes. So we actually have to produce 1-butene separately. Since it also has to be separated, we actually have 5 products here. So unfortunately, this means that the number of possible sequences has gone from 40 to 224, a little bit too much to handle. So it would be very helpful to use the heuristics we looked at before to try and reduce the space of potential sequences that need to be analyzed. So now going back to the relative volatilities between every 2 pairs, it's pretty obvious that we have very high relative volatilities for the separation of A from B and from E from F. So those 2 separations will only be done by ordinary distillation. There's no point trying anything else. The alphas are very high. On the other hand, C to D is bad news. We have here only 1.03. The minimum alpha you want to consider for distillation, it's probably didn't appear, but there's a heuristic for that too, is 1.05. This is under that. So BC would not be done by ordinary distillation. We need to look at extractive distillation for that one. And just to cut a long story short, we are actually reducing the number of separations down to just these 6 instances. A from B with ordinary distillation, E from F for ordinary distillation, B from C ordinary distillation, A from C ordinary distillation, and C from B and C from D by extracted distillation. The reason that we have here A and C is that Fouverol reverses the order of one of the components in relative volatilities. In order to do the calculation, we need to estimate the capital cost for each separator, which is actually not very good news. It means we actually have to do simulations for every separation, which means setting column pressures. It means computing the minimum number of stages in the reflux ratio using the Fensky-Underwood-Gilliland method, otherwise known as DistWo in Aspen, or the shortcut column in Unisim. We assume a tray spacing. We calculate the column height because we know how many trays we have already. We compute the tower diameter using the fair correlation, or for example, in Unisim, the tray sizing utility. This allows us to estimate the cost of the tower. The auxiliary equipment, of course, the condenser, the reboiler, the reflux drum, these have to be estimated also. This gives us a total capital investment. Notice this is why we need to already know some economics before we do this part of the course. That's why we're teaching economics to begin with. We then compute the annual cost. That means heating and cooling utility costs, and that allows us to compute the annual cost of each tower. And what we'll see in the charts in a second are for every separation, the cost that appears here on the right-hand side. Why do we need this? Because we now do branch and bound. We take your original separation, which is A, B, C, D, E, F. That is what appearing in the root here. And we take each of the branches of that root according to the first step in all possible sequences, starting from that first step. For example, we could first remove A from B. using order distillation, then B from CDEF using order distillation, then C from DEF using extracted distillation. CD has to be extracted distillation, and then remove DE from F. This sum of these 4 separating steps comes to about $900,000 a year, and we just basically systematically go through step by step using the idea of branch and bound. If we find during the progression that we find a tower that has a cost for that one tower being greater than the minimum found so far, obviously there's no point checking anything further down below it. That's why this is called branch and bound. Okay, we then move to the second. We then move to the first step, that is to remove B from C by order distillation. There are some alternatives. The optimum one is this one here. And notice that each time we find an optimal value, it replaces the upper bound we found so far. And basically you go through the whole procedure, checking through everything. Of course, utilizing the idea of branch elimination if we find a branch that has very high cost. There's no point costing these two. All right, so the students therefore have arrived at the optimal design. That's this one here, which is actually the one they were shown at the beginning of the course. So that closes that part of the promise made to the students. In the same lecture, we also cover the marginal vapor rate method. I'm going to just very briefly mention that it's faster alternative, of course, to the branch and bound optimization, as it is based only on shortcut simulation of the separation columns. It does not require any equipment costing. Therefore, it's much, much quicker to do. This is the one that we would recommend, and this is the one that what students would be using in the project, of course. And basically, it allows us to get to the same result only using shortcut column simulation, DISWU in Aspen. Okay, that covers the section on zeotropic separations. In the 6th week, we cover azeotropic systems, and here are the instructional objectives for that week of the course. So students should be able to sketch residue curves on a tertiary phase diagram given appropriate data. They should be able to define the range of possible product compositions using distillation, given the feed composition and a ternary phase diagram, which they generated in the first step. And given this information, they should be able to design a cost-effective separation sequence to separate a system exhibiting homogeneous and or heterogeneous azotropes. So the idea of residue curves, basically the idea behind it is that you basically generate an ordinary differential equation based on the thermodynamic properties of the system. It is shown in the book that this is applicable also to an actual distillation column at total reflux. It's a very good approximation, and students are learn to sketch residue curves, all right? Meaning that typically they will be given a system involving, let's say, 3 components, where in this example, we see here 2 binary azeotropes at points E and D. The sketching involves first defining the distillation boundary, then sketching the boundaries from the lowest to the highest temperature, just tracing the directions according to that, and then sketching internal residue curves according to that picture. And given this idea of the residue curve, they are learned to identify distillation regions, and they realize that it is only possible to obtain products within a certain region. Distillation columns cannot be designed to cross distillation boundaries. So in this case, for example, we have a relatively simple system involving 2 regions, but of course things can get a little bit more complicated. Okay, for example, here we have 4 regions, right? 1, 2, 3, 4. And if we are in a certain region, we have a feed point in a certain region, this defines the feasible space of distillation columns from this feed point. Students learn to identify these. This is a basic skill they need to master to be able to do design. So let's look at a typical problem. We are given a system involving two imaginary components, A and B, 30% A, 70% B. We're asked to produce product streams of pure A and pure B. We are allowed to use 2 different operating pressures for our distillation columns, and all the columns only have 2 product streams. We are allowed to use 2 mass separating agents, C and D. And here are data for the system ABC. and for ABD. So ABC, let's start with ABC. We see here the three components, A, B, the materials, and this is the mass separating agent. So here are the pure boiling points of A, B, and C. There are two azeotropes. And if we change the pressure from 2 bar to 10 bar, we notice that our problematic azeotrope, which was 50-50 AB, has unfortunately not moved as a result of changing the pressure, meaning that we are going to require the use of at least one of the mass separating agents. Here is the situation for B. Of course, this column will be identical in both cases because it just describes the azeotrope that's giving us the headache. This is the reason why we can't produce 100% pure A and B. I'm not going to go into the details, but basically you eliminate the mass separating agent D because unfortunately it doesn't allow us to produce A at all, meaning that we go to C, and if we use the separating agent, mass separating agent C, we see that it is very, very easy to do the design. What is very typical for all of these design problems is, generally speaking, we start by designing from the end to the beginning. So we identify that in the end, we need to have a column on this between these two vertices at 10 bar, which allows us to produce pure A and pure C. And the first column is going to be the one that is positioned here to produce pure B. So you start with a first column producing pure B, a binary mixture of A and C, switch pressures. And once you switch pressures to the higher pressure, we can produce A and C. C is the mass separating agent, which is recycled and mixed with the feed to give us the feed point to the first column. That's a typical problem that students would be able to solve in this part of the course. And this is actually a very simple exam problem for them too. There are exam problems are slightly more complicated than this. Moving along to azeotropic distillation. And the example, of course, the classic example is dehydration of ethanol. Well, ethanol unfortunately has an azeotrope too, right? This isn't really vodka, okay? So in order to get 100% ethanol, we obviously need to add something. And so one possibility is to add toluene and entrainer. And when we do that, we generate a ternary diagram, which is separated in the following. First, we have a two-phase liquid-liquid equilibrium region in which compositions of the aqueous and organic phases are connected by tie lines, as we know, assuming that we have a feed point to the decanter inside that region. But in addition, the azeotrope boundaries define three possible regions, of which this region is going to be important to us because it's the one that we can produce pure ethanol in. And this one is going to be important to us because it's the one we want to produce pure water in. And so this understanding naturally leads to an optimal design involving only two columns. We begin by positioning a column in the distillation region involving ethanol, and we can produce ethanol with a column that links the ternary azeotrope to pure ethanol vertex. Here is that column. Notice that we don't worry right now about where the feed to this column is coming from, but we now take the ternary diagram, which is now in the tertiary liquid-liquid equilibrium region, and feed it to decanter. This allows us to generate two products. The aqueous product from the decanter is mixed with the feed and feeds a second column in which water is produced, pure water is produced, and the second component is on the distillation boundary. And now we take this product in the distillation boundary, the distillate from that column, mix it with the organic phase from the decanter to produce a mixture which feeds the first column. And that actually closes very nicely the design. So this would be a typical heterogeneous distillation problem that would be handled by students as part of an exam question. So let me just summarize what we do in these 2 weeks of separation system design. In week 5, zeotropic separation, the key elements to get across would be the idea of the separation factor as the deciding factor between alternative separation methods and a trigger to suitable design of mass separating agents. The idea of using heuristics to narrow the research space to make it more manageable to do detailed design, and the harnessing of systematic design methods, branch and bound, but we prefer really the marginal vapor rate method because it's much quicker to implement. In the second week of the sequence, azeotropic train sequencing, again, first make sure they know how to draw residue curves by hand, then move to feasible space identification for distillation columns and tertiary diagrams, and then the use of these tools for homogeneous and heterogeneous system synthesis. That covers what I wanted to say about separation sequence. I'll now transfer control to Warren. There you go.
Okay, are we ready to go? Looks like we
yeah.
are. All right, so let
think
me
you
do
can-
this. Wait a minute, yes, I do. I want
There
to
you
do
go.
that. I want to
There
do
you go.
this. Okay, here we go. Okay, Danny, that's very nice. Hope people can appreciate the animations you have created for those sequences. Okay, I'd like to take up another subject that many people do not cover when they are teaching design, probably because thermodynamically it's just very difficult, but you learn so much from this. Second law analysis, this is chapter 10 of our book. Okay, so I want to ask the question, how do you value material and energy streams? Well, it's one way to do it is as a function of the work available from them. So this motivates the idea of their availability, thermodynamic availability. Okay, so we introduce the concept of lost work and use this as a metric to compare different versions of a process. And this is especially important when the price of energy is high relative to the capital cost of the equipment. You can do so much, you can learn so much when the price of energy is high using these techniques. Keep that in mind. Okay, the idea of thermodynamic efficiency is a result of the lost work definition, and I'll show you that at the very end of what I have to say. Use these ideas in a concrete example to teach about and evaluate a proposed refrigeration cycle process, and I'll be showing you how we do that. Okay, now, thermodynamic availability is a measure of the value of a particular stream relative to ambient conditions, okay, the environmental conditions. Any process stream that is different from the ambient environmental conditions has a non-zero value for availability. So it's important to stress that the ambient temperature is typically defined. I guess if you were on the top of Mount Everest, it wouldn't be, but for most of what we do, it's defined as 77 degrees Fahrenheit and 537 Rankine. Okay, all process streams can be evaluated relative to ambient environmental conditions. This provides a consistent metric to measure the relative value of the streams. So what you do, here's the thermodynamic availability, to go from your stream at state 1 to the environmental condition, the ambient condition, okay? So you simply calculate, okay, the change in the enthalpy and going from 1, okay, to the environmental condition. Aspen does that blindfolded, okay? Then you subtract T naught, all right? So that's the environmental temperature, okay? Then you take the change in the entropy and going from 1, 2 to the environmental condition, all right? Now, it's also useful to calculate how a stream's availability changes as the result of a process, okay? Because availability is a state function. It's basically delta A going from 1 to 2. Okay, you see this is a state function. The only thing that's different is T naught here is a constant, the ambient temperature. Okay, so we do this now for superheating a steam stream, liquefying air, okay, taking a gas at high pressure and passing it through a throttle, a valve, mixing 2 streams with different compositions, mixing 2 water streams at different temperatures to see just what is the change in the availability. Okay, now, this is key, and it's hard for me to get this across to you simply at this point. You'll have to read the book. We consider a control volume, okay, on an open system. Okay, so there is the open system. All right, this will be the starting point for the derivation of lost work. Both an energy balance and an entropy balance on the control volume will be required. It is also important to note that the lost work is going to be, okay, the environmental temperature times the change in the entropy due to irreversibility. Okay, so for this example, what we have is we have a stream coming in, stream 1. We have another stream, 2, coming in. We have a stream leaving, okay? All right, now, we're going to have heat coming, all right? So from this particular heat source, reservoir we call it, all right? We're going to have heat going to the infinite. This is the environmental reservoir at T0. We're going to have heat going this way, okay? Okay, to heat another reservoir, we call it heat sink 2. If the flow of heat goes in the opposite direction, well then, if it comes out like this, it is then considered to be negative. If it comes in like this, it is considered to be positive. We now, okay, we also have work that's occurring. So you have work now that's being done by the control volume running a turbine, say, all right? And there may be other sources in this case, but all right, we have that. So now when we do the energy balance, there will be a change in time when it's not steady state, okay, in the control volume. We ignore that in most of what we do in the chapter, okay? And here we just have the change in enthalpy flow rate of the flowing streams, okay? So we need to know what's coming out, flow rate times the enthalpy. Okay, what's going in minus the flow rate times the enthalpy, and similarly for this, that's this term. Okay, now we have to have the heat, all right? So this is now Q naught, and it would be Q naught, it would be positive if the heat is coming in there, because we're showing it here now as negative, it would be a negative number, and you get the idea. You have the summation of the heat flows to the other reservoirs and the summation of the work flows, okay, to turbines and things of that sort. You have a similar thing now for the entropy. You do what is known as an entropy balance. Okay, again, we're ignoring the dynamics here and just doing steady state. So when you do that, go to the book, you'll find the derivation of this very straightforward, I believe, and it just shows this. The work terms, this is the actual work done, plus the lost work, okay, is equal to the change in the availability of the flowing streams. We call these convective terms. And, okay, here's now the summation of 1 minus T naught times the temperature of the reservoir for each of the heat streams, okay? So these are the heat reservoir terms. And we go on now, and we look at this now just to understand the relationships here. The lost work will be 0 for a reversible process. Okay, that's an important thing to know. There will be no convective no convective streams in and out for a cyclic process. So this whole term goes when you're talking about a refrigeration cycle. Okay. Okay, the students can also use this to evaluate the individual steps within a cyclic process. We'll talk about that in a moment, okay? And then we highlight, you know, as we're teaching this, the possible causes of lost work, the mixing of 2 or more streams, the finite driving forces for transport, heat, the fluid friction and drag, and you all know, I don't think I need to go through all of this. Okay, now this, in our view, is a very important example that appears now in chapter 10. Okay, and this is where we're trying to refrigerate, and we want to keep the contents of the refrigerator here at 10 degrees Fahrenheit, and we're taking heat out to an evaporator. And we're using a propane cycle. This is a propane fluid, a circulating fluid. It's a closed system as far as this fluid is concerned. It just goes around and around. Okay, we bring up the heat. Okay, we now have a saturated vapor. We go to the compressor. The compressor then builds, okay, the pressure and the temperature. Now we're up at high enough temperature, we can go to the condenser, to cooling water. And you come around, and now you can go to a valve. and you can drop the temperature, drop the pressure and drop the temperature down and go around like that. Okay, what the students need to learn is that they can calculate the lost work associated with each of these 4 units separately. And the total lost work of all 4 units has got to be the lost work for the entire process. Okay, now then what they need to learn is you can do things to reduce the amount of lost work. Where will the most lost work occur? Across that valve. Do you want that valve there? No, you don't. You'll put in a power recovery turbine. Yes, it's going to cost you money to put that in. But remember, the price of energy is high, and we can afford to put that in for that. Okay, that's a key aspect of this. All right, and then what we do is we lower the delta T right in here. Of course, you know, that's basically by lowering the delta T, we lower the amount of lost work here, and similarly do the same thing here. You get the idea. We want the students to understand that well. Okay, then we go to define what is the thermodynamic efficiency. This is different. This is not an isentropic efficiency and so on. This is the thermodynamic efficiency. You have a main goal. Okay, if your main goal is to obtain work from a heat engine, then your main goal is to do it reversibly. That'll give you the most work. That's a positive main goal, but your lost work is so much. So divide by this and you get a thermodynamic efficiency. If your main goal is to obtain heat from a low temperature reservoir by doing work, okay, that's negative. A negative amount of what you want to do in that case is do as little work as possible. Okay, this is going to be a negative main goal. So you'd put that in, you put that here. This is negative, and the lost work itself is also, it's positive, but it's going to be negative. This here. So what you have is a ratio which is somewhere between 0 and 1, and that's the thermodynamic efficiency. Okay, when you have a negative main goal. Okay, that's important for the students to understand that, and it is often difficult for them to understand it. This part of the course is quite difficult for a student, but we think they learn a lot when they do it. So I'm going to leave it at that, and that takes us now to the second 15-minute break, and so it's Bamrung Sungneon who is going to handle this break. Okay, just a minute. I'll get rid of this.
So thank you very much, Warren and Danny. So now Bamrung can start with the discussions, and we will take the questions from the point we stopped last time. We are running a little bit late, but I hope we can make up in the next section where the lectures could be reduced a little bit. Okay, go ahead, Bamrung.
Thank you for having me here, and let me introduce myself. I have been working at SCG Chemical. Yes, I have a background about the process commercialization over 10 years, and I think we have many iterating question here, and I just for some question I think I should answer in terms of industrial will. Let me share my screen. Okay, thank you for the question from the Sarah. Sorry if I pronounce the name wrong, and Asar and Kenya. For the first question is, it is possible to cover theoretical aspect related to the product design, process design, synthesis, equipment design, mechanical design, P&D, UAI, economic things, safety thing in the design. Yeah, for me, the first thing you should know about that the role of the engineer is we find the benefit from the nature, right? This is our track. We try to make money from the nature. We learn about the theoretical to understand behavior of the nature, and we predict it, and we use it to make the money, right? In the engineering, for example, yes, we can use the or thing in this webinar in the process design. And when the engineer, we learn about, we cannot learn every phenomena in the nature to use it in the design in the real life case, right? But we use the major phenomena to use the design and predict it, and then we use the safety factor things to design to cover the range in industrial. For me, my answer, yes, we can use it. For example, we learn about the distillation. We know about the tendency of the refractory ratio. We increase the refractory ratio, right? And the purity of distillate is quite high. And for in the real case, right, we also use the tendency of refractory ratio is follow the theoretical. Yes, we can use it. And I think the question I can answer. And from the answers, in my understanding, the heuristic were conceptualized based on the experience created from the community chemical and conventional chemical engineering unit process. May you share some reflection where the heuristic and may possibly evolve from the process based on biopharmaceutical vaccine and I think the new platform like the hydrogen electrolyzer. For me, I work in the the chemical, right? And my real task is about the find or scouting the new technology for the SDG, the chemical. We find many options, not only in the community chemical or conventional, the engineering unit. For my experience, the difficult between for example, for petrochemical, biopharmaceutical, and vaccine is quite different, but the step of work, the step of thinking is quite similar in the process design. You can, you know what you try to produce in the market. You know what is the reason, right? You need to produce the product, something like that. For example, I have experience about the solid handling, but it's quite different from petrochemical, right? And the hard thing about is the reactor. It is not the separation. For the industrial, for the petrochemical, it is hard thing about the both reactor and separation. Yes, but for me, for the heuristic or about the experience, for the engineering, we care about the benefit. Which process can provide the maximum benefit to the community? It is the best process. Yes, I think it's we for my understanding, yes, we can use the step of work like the professor said in this. For the next question about from the Kenya. In my experience as a bioprocess chemical engineer student some years ago, we typically design the process or pen benchmark with the existing process or just the patent, the publication. It's not desirable compared to the heuristic approach. If we do okay to benchmark, if we can provide our understanding of heuristic and why the flow sheet designed a way as well as the provide the change when necessary. Yeah. Yes, when you try to design the process, you have to the separate the two things. The first thing is about the idea how to generate the process and about the calculation from heat and mass balance from the process, right? And I think for me when we do the technology, okay, we try to scout or read the many publication, many the patent. Some patent the objective of the patent it is not only about the construct the real plant. You know, the patent you design the process. Sometimes you cannot use in the real pen, right? But you try in some company try to build a new the process, sorry, and try to different and try to just filing the patent. It is not launched in the commercial. It is it depend on the direction of the company. If you review many patents in the same process, you provide the many process, many unit of the operation, the process identification, right? That yeah, is depend on the objective of the company.
Bamrung, can I interrupt you, and maybe you can ask if Danny Lewin or Warren Seider has some comments on these questions very briefly, and then we will move on.
Well, the second question, or what Assad had to say here, I can say a couple things. So, the issue about the heuristics, as you're moving to biopharmaceuticals or vaccine manufacturing, well, are they different? Yeah, I mean, we go through those steps, but when you look at what we have to do for the tissue plasminogen activator, we have very little to do in way of heating and cooling, because almost everything that you did in that process, okay, certainly in the cultivators, the reactor sections, I mean, everything was done at 37 degrees Fahrenheit. There's very little in the way of heating and cooling there. And similarly, in the separations, it was very important not to damage any of the protein that we were making. And so we had to stay down at temperature. So we had to be at about, as close to freezing as possible without getting freezing the water. So about say 4 degrees centigrade was what typically. So the point I'm trying to make is that for that kind of a process, for the biopharmaceuticals, temperature issues are not anywhere near what they are in a conventional chemical process. That's one. Vaccine manufacturing, I know a little bit about that because at the University of Pennsylvania, the mRNA vaccines were much of the technical development was done in the hospital at the University of Pennsylvania. Okay, so it turns out that a key thing there was to be able to take the mRNA molecules, which are the ones that need to be able to grow in the vicinity where the virus is active in certain cells. You have to have a way to carry the mRNA across to those cells. And if you don't do that, you're going to get inflammation and it won't work. And they worked for years to try to figure out how to do that. And in the end, it's nanotechnology that did it. It's these little nanoparticles that carry the mRNA to the cells. So, all right, the designs are different. They are. The steps are the same, but the heuristics will be different for those kinds of processes. And I'll leave it at that.
Danny, you have any short comment?
In the interest of space, I think we should move on. There was
Okay.
one question. There was one question which hasn't been addressed. One of the participants asked about the minimum prerequisites for a design
Yes.
course. I can maybe just relate what we do at the Technion. There are actually 6 prerequisites, but we teach 2 control courses, 2 reactor courses and 2 thermo courses. So in my design course, I require a minimum of at least 1 thermo course, 1 reactor course, a course in multi-stage separations, and the simulation lab. Those are all prerequisites. Any student who doesn't have those 4 courses under his belt is not allowed into the course. He has to complete the prerequisites first.
Okay, very good. I will just read out one comment that afterwards can be discussed if you have any answer. Is from Chinmay. He's actually from Buet in Bangladesh. He says that he enjoyed his design course very much because somebody from industry was also participating and giving part of the course. So he is asking, how can we involve experienced process engineers in the learning experience of student? Introducing process design standards can be important. But I'm just reading it out, think about it, and we can discuss it later.